Morning, everyone. So today we're going to be looking into our second chapter in Chemistry 12. This is going to be a chapter on dynamic equilibrium. So if you can just start a fresh new page here, Unit 2. We're going to look at equilibrium as a concept. Just to introduce this a little bit, basically we've been simplifying things a little bit. We've been looking at, for example, A and B. The chemicals we put on the left side, we refer to them as reactants. We draw this forward arrow and basically we say A and B somehow combine together and end up forming products. The simplification we've been making so far is we've been assuming that all reactants, all the time, they go to products. We talked about this being the forward reaction here, but we've been assuming that things go to completion. In our last chapter, we started plotting this out on a potential energy diagram or an enthalpy level diagram. So you can plot here the potential energy against the reaction axis here. For argument's sake here, let's say this is an endothermic reaction. So we start off with our reactants, A and B. We know we end up with products with a higher energy here. We spent the majority of the last chapter talking about there being an energy hill. There's an activation energy, a minimum energy you need just to start breaking bonds and forming bonds. The collisions need to come in with the correct geometry, with the correct energy for them to actually form this activated complex. And only the particles that were fast enough in A and B can actually get over the hill. In Chem 11, we were focusing more so on the delta H. We didn't really care about the rate of reaction, this energy barrier that I'm listing there, but we cared more about the delta H. Well, overall, this delta H, bigger positive number minus smaller positive number here, the delta H here is positive, which would imply that this reaction here is endothermic, right? What I want to show you in this graph here is we'll see that the same activated complex, for the activated complex, essentially it's the A and B smushed together, right? It's that transition state. We use a symbol there. What you will notice here is the activated complex, not only is it going to be a temporary species in the process of rearranging bonds, all that is still true, you'll notice I could actually make the activated complex if I say started out from C as well. So if I start out from C, in fact, for an endothermic reaction, the energy barrier is actually a lot lower in the reverse direction because C actually stores a lot more energy to start off. All that to say here, this reaction, because I could go forwards and I can create the activated complex, or C can actually recreate this complex and come back the other way, reactions are what are said to be as reversible. So I can just rewrite it if you like. So you can go C is becoming A and B. Just conventionally here, we're going to always talk about the left-hand side to be reactants and the right-hand side to be products. Make sure you do an arrow. And this one here is going to be for the reverse direction. Now, especially for reactions that are like this here, I don't always want to have to write that out sort of left to right and then flip it around. What you can do is you can just sort of summarize that and you can say, well, the first reaction, A and B, going left to right, the forward reaction was just forming C. And then if I want C becoming A and B, it's sort of like taking the products of what I specified and becoming reactants. And this is now the reverse reaction. So the reason why we plot it actually against the reaction axis here is because we can read this left and right. Again, in general, we say reactants on the left and we have products on the right-hand side. So this is a new symbol for us here. At first, this symbol just implies to us reactions are reversible, which means reactions can be undone. So reversible, they can go both ways. And in fact, we're going to be using the symbol here to introduce our concept on equilibrium. So not only do I just want to suggest to you, yeah, we could go forwards or we could go back. Naturally, systems would tend to a situation of equilibrium. When we actually use the symbol, it actually implies equilibrium. The equilibrium that we do in chemistry here is a situation called dynamic equilibrium. Let me just specify some of the main notes here. They always ask the question, well, what does it mean dynamic? The dynamic part of this says things continue to occur. Even though we are at equilibrium, even though we've hit some sort of balance, in this case here, the things that continue to occur are the reactions. That's usually on the microscopic level. So usually they just mention it this way here. The microscopic reactions continue to occur. So even at equilibrium, things are still happening. Reactants are still becoming products. A and B are still making C, as C is still making A and B, right? So those are still occurring, forwards and reverse. However, we are in equilibrium. Equilibrium, again, has this notion of there's some sort of balance, right? And the balance that we're going to talk about is macroscopically. When you just look at this from the outside, macroscopic properties, things that you can observe, physical characteristics, things like that, the macroscopic properties, they remain constant. But I want to emphasize here, in time. So if I look at it right now, I come back, look at it half an hour from now, it doesn't look like things are changing. How is it possible that both of these can be true? How is it possible that microscopically forward reaction is still occurring and yet outwardly nothing seems to be changing? Nothing seems to be differing in my system. The only way for this to happen is for a conclusion here. We'll see an example of this later. The conclusion is, yes, while you still may have a forward rate, yes, you still may be converting reactions to become products, if the forward rate equals the reverse rate, that can keep both of these things here true. So, just as an analogy here, let's imagine we went to go watch a hockey game. I have my team here on the left-hand side here. I can have any number of players on the bench, right? They're just waiting for their line change. At any given time, I have 3 on the front line. I have 2 defensemen, right? I'm going to ignore the goalie for now. So, as you watch this hockey game, you would expect, while the game is going on, you should always have 5 players on the ice. And yet, if you've been to any hockey game, you're going to realize, wait a second, it's not always the same 5 players on the ice. If they had to skate for the whole 60 minutes, they'd tire themselves out. In fact, every minute or 2 minutes or so, they do what are called line changes. So what's happening here is when they have a chance, these 3 frontliners, they're going to jump off. As long as 3 people jump on to take their place, they can still do the jumping on. They can still do the forward and the reverse reaction. But as long as their rates are matched up, 3 go on and 3 come off at exactly the same time, overall, I'm going to still have 5 players on the ice. Likewise here for the defensemen here, there's only 2 of them. So whenever 2 go off, as long as 2 come on in their place here, we're going to always maintain this system here. So in the chemical context here, it's totally possible. I like this analogy because let's say the players on the bench are your reactants. It's totally possible that given a hockey game, I actually have way more reactants. The concentration of reactants is actually way higher. Maybe the concentration of products here is only the 5 players represented skating here. Notice the concentrations between reactants and products don't have to equal each other. I want to make that note here. Even though the rates have to be true, the concentration of reactants does not have to equal concentration of products. If it does, it's by coincidence. But I thought it has to be constant here. I didn't say they had to be constant with one another. I didn't say they had to be equal to one another. Like we could have some 20 players on the bench, and we only have 5 players on the ice. I said they're constant in time. So at any given time, when you're watching first period, second period, halfway through the third period, things like that, the concentrations, the number of players on the bench should always stay the same, and that's a different number than the number of players on the ice, which should always stay the same. So in point number 2 there, concentrations here are constant. Usually we think, oh, constant equal, right? Well, no, it's not equal to each other. Concentrations are constant in time. That means the concentrations don't change as you watch this hockey game happen, right? So that's how we sort of introduce dynamic equilibrium here. Things are still occurring, but because of this main statement, the forward rate has matched to the reverse rate. That can keep both of these things true. In physics, you're also going to do a situation of equilibrium. However, in physics, we talk about a situation called static equilibrium. Static just implies, yep, it looks like things are in balance and nothing is really changing. That's because nothing is changing. So if I hang up a beam with strings and whatnot, basically if that beam is just floating in space because all the forces have canceled out, it's because really nothing's happened. This time I may have a situation here. Let's say we have, I take a salt and I basically want it to dissolve in water. At the beginning, the salt is all salt crystals in the lattice here. At the beginning, it's just going to keep dissolving. It's going to keep breaking up. Eventually, though, what would happen is some of these salt crystals are going to collide together, and they're going to actually recrystallize out, and they're going to end up reforming solids here. Microscopically, things can still occur. Even though it looks outwardly like it's saturated, it looks like nothing's changing anymore, as long as the dissolving happens at the same speed as what's called the recrystallizing, as it actually comes back out to become a crystal, as long as those two things are equal, the concentrations are going to stay constant in time, although the amount of salt in the block and the amount of salt in the water may actually be different. Right? So a couple added notes I want to do here. Because we need the sort of reversibility of the reaction here, especially if a reaction produces gas, I don't want to be an open system. I don't want the gas to actually escape. If it leaves, it has no chance to then re-enter the solution. So usually we do imply here, we look at equilibrium systems when we're at closed systems. We could hypothetically be an open system as well, but make sure there's no gases that are evaporated. So closed system just sort of minimizes that there. If you're in a closed system, even if there was a gas that was vaporizing off, the gases will still stay in close vicinity of it, and they can actually manage to get back in eventually. Closed system, we're going to talk about sort of temperature as another factor, not just to change how fast the reaction occurs. Temperature is a factor that can change equilibrium. So when I watch a hockey game here, I expect there to be 5 players on the ice. If I watch the same hockey game at a different temperature, maybe it's the same sort of hockey games, the same teams competing against each other, but maybe it's a game which I have 6 players against 6 players or 4 players against 4 players. The equilibrium will still establish. It'll still hit this balance. It'll still hit this macroscopic properties are constant. However, I'm going to be a new equilibrium at a new temperature. So what I'm going to specify here is we're going to typically be a closed system. We're going to keep, for all intents and purposes here, we're going to keep at a constant temperature, because what's going to happen, I'll write that down for you here, we actually hit a different equilibrium. I'm going to write EQM for short for equilibrium, different equilibrium at different temperature. So it's not that you couldn't reach equilibrium at any temperature, but the equilibrium at 20 degrees is different from equilibrium at 50 degrees. We'll see this in due time. One other added note here that's not immediately obvious is the fact you could reach this balance situation, this dynamic equilibrium. It doesn't matter whether you start with all reactants or all products, or some mixture as well. Basically, systems that will go towards equilibrium will naturally head there. You don't need to worry. It's always going to hit the same equilibrium at that same temperature. So back to our hockey game analogy here, at the beginning when the hockey game starts, right, before we actually set up and actually have 5 skaters on the ice, I get the whole team. Like, let's draw it on this side here. I get the whole team to actually do a quick skate here, do a quick warm-up here. I may have all the players on the ice. So maybe that's all products right now. I don't have any reactants. But then as we get ready for the game, most of these players are going to start benching themselves, and then the 5 players that are on at that time, they're going to stick around. So that was a situation where all the skaters were on the ice, the entire team was there, and then as I approach equilibrium, we're going to set up until we have 5 players on the ice and most of the team on the bench. In a similar fashion, I could have had all the teams on the bench. All the teams are reactants, nobody's on the ice yet. They can also say, oh, now we're ready for the game here, let's send 5 skaters on. I can hit this equilibrium from either the reactant side or the product side. So let's just do the chemical context here. As an example, we're going to do 1 N2O4. This is dinitrogen tetroxide here. I'm going to so far just write the forward reaction. N2O4 is supposed to decompose to become 2NO2. Both of these are just gaseous. Right? You can avoid sort of the hassle of solids for a little while. Essentially what's happening here is I'm starting off, let's fill my container with just pure N2O4. Right? So in this case here, this is all reactants. I have absolutely no NO2s, no products around. What this reaction specifies then is, well, over time, this N2O4 is going to steadily start becoming NO2. So over time, I don't know which exact molecule is going to decompose next, but over time, some of these are going to break off. Oh, yay, I become 2 NO2s. Or maybe this one starts becoming NO2s. Right? So that's just a forward reaction. I'm generating some of my products. This is going to head toward a situation called equilibrium, EQM. Our equilibrium is going to have to contain both reactants and products. So at this point here, not all the N2O4 has actually reacted. I still had those 2 there, but now I'm left with perhaps, well, the NO2 is left behind by the first particle, the NO2 is left behind by the second particle. At equilibrium, I should always have both reactants and products present. And if you think about why that's the case, well, for me to still have my forward and reactions occurring, well, I need to make sure that I still have the ability, well, I still have still some reactant here, this NO2 here can still become, this N2O4 can still become 2NO2, the forward reaction can still occur. However, at equilibrium, we said the rates are equal. As that N2O4 starts breaking out to become NO2s, before that ends up just completing, maybe 2 of these NO2s are going to recombine together and they're going to become an N2O4 again. So for me to still have my forward and reverse reaction, we need to have both reactants and products present. Essentially, the rates have to equal. So N2O4 becomes 2NO2 as 2NO2 becomes N2O4. That's what we mean by forward rate equals reverse rate. the rate at which the N2O4 decomposes is the same as the NO2 synthesizing and joining together, notice that their rates are equal. That's the key in this chapter, right? The speed at which we're doing the line changes are the same. The concentrations are going to be constant in time. If I plot for you here, well, how much overall N2O4 do I have as this is occurring? Well, I had a system where I started off with 2 N2O4s, even as one more N2O4 breaks up, because the other one ends up recreating N2O4, the concentration of N2O4 is constant in time. I'm going to always have, let's say, 2 particles of N2O4. Likewise, the NO2, we had a situation where we started off with 4 NO2s. Oh no, I'm losing 2 NO2s, but this N2O4 is also recreating 2 NO2s. At the end of the day, we're going to have the concentration of NO2 also constant in time. So as you watch the system occur, because their rates are equal, macroscopically it looks like the amount of N2O4 and the amount of NO2 is exactly the same. However, the one conclusion I want to hit for you here is notice, in this picture as I sketch it for you, notice the N2O4 doesn't have to equal the NO2. It's like that hockey game. I don't need to have, just because 5 players on the ice, I need to have 5 players bench. No, I can have many more players bench. It's just that they have to stay fixed in time. I'm going to make this note here. Even though this is true, the concentrations have to be constant in time, the N2O4 does not have to equal NO2. It could, but chances are it doesn't. So they don't have to equal each other, the number value. If I have 2 particles of N2O4, doesn't necessarily mean I need to have 2 particles of NO2. In this case here, just for comparison, I actually had, let's say, 4 molecules of N2O4, 4 molecules of NO2, whereas I only had 2 molecules of N2O4. And I chose this example here because this one here actually gives us a colorful product. So I believe the N2O4 is actually like a brown colored gas. So essentially what's going to happen is we start off with a really deep brown solution because I have a lot of N2O4. As the N2O4 slowly breaks up to become NO2, as I lose the chemical that actually shows a brown color intensity, we're actually going to get lighter and lighter intensity. So outwardly, this solution here is going to be a little bit lighter of a brown color than beforehand, but the light color is going to stay constant because the chemical that was making that brown coloration is actually staying the same amount over time. We can also reach this situation from products. So let's say instead we started from products. So I start from the end and I work backwards. My products are actually just NO2s. So just fill a container with all NO2s. I don't necessarily care how many, right? So you have NO2s just sort of completely filled. I know I'm not at equilibrium because so far I only have the reverse reaction. So far I only have the products, which they can collide together, they can recombine, they can go backwards to become N2O4. So slowly over time, these guys here are going to start becoming N2O4. It's going to start making that chemical that starts looking like a brown color. And basically, we're going to end up hitting the same equilibrium. As long as we're at the same temperature, we're going to end up hitting the same equilibrium. Right? So at least I wanted to just suggest to you, well, this is what we're going to be talking about through the next couple classes or so. Before we actually zoom in on equilibrium systems directly, we want to figure out which systems are like what we did in Chem 11, which systems just go 100%. There's actually no way that this thing here can come backwards, which systems don't react at all, no reaction, and which systems will actually end up as equilibrium. So today we're just doing some more preliminary work here. We'll study equilibrium for the rest of this chapter, but let's first ask ourselves the question, how can I predict which equations will actually hit equilibrium? So we're going to do this as a section here on spontaneity. If something is spontaneous, it just occurs. So essentially we're going to use this whole notion, the Rxn, the reaction occurs naturally. Sure, it still needs that energy input to get over the activation barrier, but you basically don't need to help it along. You don't need to force it to happen. You don't need to use electricity to recharge the battery, something like that. The reaction naturally occurs. Turns out for spontaneity, or turns out to predict which systems will hit equilibrium, which systems won't, we actually need to look at 2 factors. First factor we're very familiar with in our reaction kinetics section here, that's the whole notion of enthalpy. For some reason we use H for that. Enthalpy refers to the energy in the system, right? It's sort of measuring the heat content, how much stored energy the particles have. So let's just sketch, for example, here. Let's do an exothermic reaction. A becomes B and spits off heat, right? So I'm going to draw an enthalpy level diagram or a potential energy diagram, different names for the same thing. A is going to start off at some higher energy. As A becomes B, it ends up releasing off this heat to the surroundings. So I would expect the B to be lower. That's what guarantees me to be an exothermic reaction. We still have that energy hill. Any heat that we end up releasing off is just heat loss to the surroundings. Using the whole notion, well, it's energy is what you need for work. The more energy I have, the less stable I become, right? That's why the activated complex was so unstable. In this case here, you can always say nature tends towards lower enthalpy. If nature had its way, it wants to minimize the energy because minimum enthalpy equals more stable. Right? So instead of the system having this much energy where a lot can go wrong, I'd rather have the reaction go forwards because B is a lower energy. It's lower down on this graph here. It's going to be much more stable. So I prefer, does A want to become B? Well, of course, because it's going to be producing a lower energy compound. It's going to be producing a more stable compound. Now, what if I did an endothermic reaction? So what if I did like C plus, let's do energy, it becomes D. Endothermic reactions based on this argument, these things here shouldn't happen at all. Because endothermically, I'm going to start off with C, I end up D, which is higher in energy. In fact, the energy barrier is even higher than that. Why would nature actually want to go forwards? Because I'm going from the low energy side here. Why would I want to absorb energy, steal energy, store energy into my molecule and actually become D? It's just that we actually see, some exothermic reactions, most of them are spontaneous, most of them just happen. Think about burning reactions, those just occur right away upon you sparking the reaction, upon you triggering the activation energy. But some endothermic reactions occur. So if enthalpy was the only story, it doesn't make sense why an endothermic reaction occurred. Nature would still tend towards being on the low energy side. If I put a bunch of C in the box and I have a bunch of energy left over, C doesn't want to grab the energy because then it's going to become a less energetic state. Right? So this is a general conclusion I want you to take note of. Nature tends towards lower enthalpy. If nature had its way, the way I picture it here is pretend you're the activated complex. If you had a decision whether you want to fall to the left or fall to the right, nature will tend to fall towards the side that has the lower energy. And if you notice, based on this here, the lower energy side always points towards the exothermic direction. It always points towards the heat term, right? So when we say here the system prefers the exothermic direction, right? Because whichever way I point exothermically, I'm going to end up creating compounds that actually have lower energy. System prefers the exothermic direction, pointing towards the heat term. Right? And that's just something we just observe here. Well, for an exothermic direction as written, which side is lower energy? If you point an arrow towards the heat term, that's the lower energy side. This time the heat energy is on the left-hand side. The exothermic direction, what's endothermic going forwards is exothermic going backwards. The exothermic direction is going that way. So using just energy as an argument, you're going to decide to point towards the heat term. Now you have to be really careful, especially as we get to some questions here. Sometimes they're going to list off a reaction for you, and all they're going to ask you is, what happens to enthalpy? I've sort of given you the conclusion here. I've sort of said, if enthalpy had its way, if nature got its preference, nature would prefer the side with the heat term. But sometimes nature doesn't get its way. So if I forced you to say, well, as C plus energy is becoming D, what's happening to energy? You can still say nature wants to point towards the heat term. The lower energy side is my side. But if you force me to describe C becomes D, I can say, well, the enthalpy has increased. And you say, wait, I thought energy doesn't. You're right. Energy doesn't want to increase. But as you've written it, you're sort of suggesting that it's increasing. Right? So just be careful that we'll see that a little bit in the questions here. The second feature here, which sort of saves the day, how come an endothermic reaction would occur at all using an energy argument, a stability argument? There's no reason for me to spontaneously become something that's less stable. The other side of the coin is a guy called entropy. And entropy, we're only going to get scratch the surface of this one here. Entropy, we're going to use capital S for this. And entropy is actually a measure of the disorder in the system. There's a couple other words that are associated with this disorder. Sometimes we refer to the entropy as the randomness. Sometimes we refer to it as the chaos, the chaos. Okay, so how messy the system gets, right? And this one here, again, we're only doing a really simplified picture of entropy. The best way to talk about entropy here is just looking at the physical state of matter. We're going to have a relative order for entropy. Let's picture a solid. So solids, we know kinetic molecular theory, the particles are all tightly packed, they're all just vibrating in place. As a solid, we would say in this lattice structure, we are very ordered. We're very neat, even though this one here is sort of shaking in place. It's not a neatness of 0, but we are fairly patterned, one above the other, everything is nicely arranged. Because entropy is defined as disorder, something that has high order, we can say it has low entropy, okay, low S. Low randomness means you're very ordered. Well, what about liquids? Well, as you get to liquids here, it's the same number of particles, but now they have a little bit more energy. Now they can start slipping and sliding past each other. We sort of lose that order of the lattice. We're not tightly packed together. We're now sort of, as you knock the beaker over, right, the liquid will just sort of take the shape of the container. The sort of chaos in the system is increased. So as I have a greater than symbol here. Liquids tend to be more entropic, higher entropy, more chaotic than solids. We're going to have this even less than an aqueous solution. Be careful, back in our last chapter, we had actually aqueous as actually the fastest reaction if we have nothing else to go on. In this case here for aqueous, essentially we have our pure liquid. We still may have the same 6 particles there, but I've now started dissolving other chemicals. And what you're going to find here is mixtures are more chaotic than any pure substances. So think about you go into your room one day and you have some shirts and you have some pants. Well, you can make more of a mess. Oh, throw your shirt over there, throw your pants over there. Versus if you go into your room and you only have shirts, you can only make a sort of limited mess. If you have many particles, I can have all those red particles on the one side, I can have all the red particles on this side, some on this side, some on this side. There's more ways I can sort of set up the system, the more chaotic the system. By a long shot though, when we get to gases have enough energy, and these ones here are now going to spread throughout the container. Now this one here is going to be the most chaotic, this one here is the most random, this one not only has the highest energy, this one here is the most disordered. Right? So based on that, we can actually make a prediction. Okay, so if I just look at the state of matter, I can figure out which one is high entropy, which one is low entropy. We're going to use S for disorder, and remember high disorder would be for the gaseous state. In the science here, if I, again, gave you the sort of solution, well, nature tends towards which one? Systems tend towards what? In this case here, in the second law of thermodynamics, systems or nature tends towards having maximum entropy. Given its choice, entropy goes to a big value. Things naturally unwind, things naturally get more chaotic, they don't get more orderly over time. You see this with your rooms here. I'm sure none of you go home one day and be like, I'm going to make my room messy, right? Let's say your room is squeaky clean, and then one day, I'm just going to leave my shirt over here. Oh, yeah, just that one shirt, that's okay. Oh, and then I leave my pants over there. I can leave my book bag over there. Oh, I'm going to leave this on the floor. It just naturally happens over time. You're actually obeying one of the laws in our universe. Next time your parents tell you to clean your clothes, you can be like, I'm just following this entropy rule here. Things will tend to become more chaotic. Of course, your parents can then say, no, like you're going to have to clean your room here. Again, it's a scientific law that in the time and energy you spend to actually clean your room, somewhere else in the heat that you're actually losing to the surroundings, somewhere else is becoming more chaotic. We're always fighting this sort of losing battle. So for us, how do we decide which side is the more entropic case? We want to point towards the side. So nature, if nature had its way, nature points towards the side with more moles, right? The more particles I have, the bigger the mass I can get. More moles of the most random phase, the most random state, right? So I'll give you an example of this one here. Even though somewhere along the way it does have to do with energy here, we can just talk entropy. We can just talk the amount of chaos just from looking at the states. So let's say I have A as a solid, becomes B as a gas. I want to know what happens to the entropy. Which side has higher entropy? And all you would do is you look at the order and you say, well, gases are way more chaotic than solids. This side here is the higher entropy case. And since nature wants to go to the high entropy case, based on entropy, I'm going to want to go in that direction there. Well, what if I had, let's say, C as a liquid, 2D as a gas, and this is going to become E as aqueous. They propose the reaction to you. Let's decide which way nature wants to go. So imagine you were the activated complex. You're sort of midway in this arrow here. What's the most random phase on the right-hand side? Well, aqueous. Oh, good. The mess here can be very chaotic, very random. So that already has a very high chaos. But in this case here, I actually have gas. Now, what about the liquid? Well, if I already have gas, this is going to be way more entropic than liquid. I can, for the time being, ignore that liquid. I can just say, well, I have aqueous as the most random on the right, gas as the most random on the left, and in fact, I have more gas molecules here. The side that actually has the maximum entropy will actually point in this direction. If nature had its way, it would tend towards the left side, regardless if this reaction were endo or exo. Now, again, what if I force you to describe, no, for this exact reaction, what happens, let me write this in words for you, what happens to this S in the forward direction? Now, we know what nature wants to do. Nature always wants to maximize entropy. We've actually already decided maximum entropy side is the reactant side. But what if I now force you to describe, nope, C is going to collide with 2D. As these things here become E, what happens to your chaos? Well, if the maximum chaos is on that side, I'm actually getting more order than on this side, the entropy actually decreases. And then again, you'll say to me here, wait, I thought second law, I thought entropy increased. You're right. Entropy does want to increase. Entropy does want to go to the left-hand side. It's just that they're forcing me to describe the forward arrow. Nature wants to stay on the reactants, but if the reactants end up going towards products, it's like the entropy decreases, not what nature wants to do. It's totally possible we can actually have the same most random state on both sides. So let's take F as a gas. Let's react it with 3G as a gas, and let's say it becomes 2H as a gas. So first thing you do is you look for the most random phase. This time it's gas on both sides. Then what we're going to do, we're going to decide which side has more moles. This side here has 4 moles of gas. This one here only has 2 moles of gas. So this time I couldn't decide based on the state of matter. It's not like gases were more entropic than liquids or aqueous, things like that. This time I'm just going to look at the numbers. And I'm going to say, can I make more of a mess with 4 articles of clothing or 2 articles of clothing? Well, again, the more particles I have, the more messy I can get. So again, the best way to do this here is state what nature wants to do, maximize entropy, and you can point towards the side. This side has more moles of the most random phase. That's why it's the maximum. Now, what does this have to do with equilibrium? We'll end off with this here. Again, in this case here, we're doing some sort of preliminary work here. Let's say I gave you this reaction, 2NO2 as a gas, and the forward arrow becomes N2O4 as a gas, and this one I'm totally making up an energy value of 10 kilojoules. Right? What you're going to do is you're going to test, based on this reaction, is this likely to hit equilibrium? Is this likely to go all the way, or is it likely to go 0%? Again, our 2 features are just enthalpy and entropy. Remember, we're starting at the activated complex. In terms of energy argument, we always want to minimize enthalpy. Minimize enthalpy means more stable. That's the direction I want. And we had written earlier, the minimum energy is pointing towards the heat term. The heat term is on the right side. Nature wants the system to go to the right. For nature, for entropy, for this amount of chaos, again, inherently it has something to do with energy, but let's just think in terms of disorder. Entropy tends to maximize. We tend to want to get more chaotic. We want to get more messy. So what we're going to do is we're going to do that ordering of states here. Both of them are gaseous. But this side I have 2 moles of gas. This side, we have maximum chaos on the left-hand side. When you have a system set up like this, well, what is the system supposed to do? If it goes forwards, it becomes more stable. Yeah, let's all go forwards. But the problem here is if I also go forwards, I'm also going to lose in disorder because the maximum chaos is actually on the reactant side. Whenever this situation happens, the system, the reaction, will reaches equilibrium. Not necessarily right away. We're going to do problems later on. Well, what happens sort of in the in-between as I get towards equilibrium, but eventually you hit equilibrium. Most reactions will take on the order of maybe a minute to hit equilibrium. Some things may take hours to reach equilibrium or even days, right? But naturally it hits equilibrium, and it's this balance between, I want to go to the other side because this side here is more stable, but I also want to keep some reactants because this side is more disordered. Let me do one more reaction for you here. Let's write this reaction here. 2NH3 becomes N2 and 3H2 plus heat. Right? It's actually not the right reaction here, but let's just say for argument's sake here, that's what happened. what we're going to do is we're going to test our properties. So minimum enthalpy points towards the heat term. Well, heat term, that's the exothermic direction. I want to go to the right-hand side. Well, what about maximum entropy? In this case here, for maximum entropy, we want to look for the most random phase here. Sorry, I forgot to mention that these guys here are all gaseous. Again, 2 moles becomes 4 moles. Well, of course, the 4 mole side here, this time, there's no reason for me to stay on the reactant side. If you put these reactants on the left-hand side here, they're going to prefer to go to the product side because that side is more stable. And they're going to also prefer to go to the right-hand side because that side is more disordered or more chaotic. And things naturally get more messy versus the nice order that I have on this side. So in this situation, when both factors I'm looking for spontaneity, both of them point forwards, I can say this reaction goes to completion. And for completion, we can use terms like 100%. What's completion in one direction here is actually 0% the other way. If I actually pumped N2 and H2, given this setup here, they would have no reason to form NH3 because then they would become less stable going left, and they would actually become more orderly, which they don't want to do. So what's 0% in the reverse direction is because it's 100% going forwards. So in the worksheets here, you get some practice. You're going to decide what nature wants to do. You're going to point these arrows. Anytime they compete against each other, doesn't matter which factor points which way, but as long as they compete against each other, they're going to hit equilibrium. We're going to spend the rest of this chapter looking at, once we hit equilibrium, then what? All right, so just try that out here. If you have any problems, just let me know. Thanks, guys.